afternoon or good morning to all of you. It's nice to have you all here for this webinar, which is primarily going to be concerned with DRBD performance tuning considerations. We're going to be giving you a quick rundown of the most important things to watch out for in terms of DRBD performance and some DRBD tuning tips. We're going to be alternating between sort of a little slideshow outlining general concepts, and we will also show you some live demonstration on one of our demo systems here. So what I'm going to be starting with is a quick slideshow, or the first few slides of a slideshow here, which I'm going to be sharing in just a second. Hang on, bear with me. And there we go. I hope you can see that okay. But before I actually get into that, I have some very, very exciting news to share with you, primarily being located in the Americas region. We have a brand new addition to the Limbit family, which we're very, very proud of, which is Limbit USA LLC, which is fully operational as of next month, September 2008, which is incidentally just next week. Limbit USA will be operating out of Beaverton, Oregon, and will be covering the entire area of North America, meaning the United States and Canada. So for you customers out there in the U.S. who always hate the fact that we sent you Euro invoices and so forth, and you were having trouble with the IRS for having to withhold taxes and so forth, all of that is gone now. So if you make use of the services of Limbit USA, you will get your dollar invoices, no more IRS crud to work out. And we're very, very excited about this latest addition to the Limbit family. And from Limbit USA LLC, I have two panelists joining me today. That's Kevin Smith and Brian Hellman, who will be working as technical senior consultants for Limbit USA, and will be providing consultancy, integration, and support services, as I said, for all of North America. Brian and Kevin are going to be supporting me in taking your questions today. Those of you who are previously unfamiliar with WebEx, you have this nice little handy Q&A window to the bottom right of your screen, where you can fire any and all questions that you might have at Kevin and Brian. When I'm through with my talk here today, which is going to last about just around 45 minutes, I'm going to be joining Kevin and Brian and taking questions, and we're going to be having about 15 to 20 minutes time after I stop talking in order to be taking your questions. So much for the exciting news that I wanted to add here before the actual start of the talk. So what we're going to be doing here, and what we're going to be giving you, is a quick recap on how DRBD actually works and what it means in terms of performance aspects. We're going to be talking about the two aspects of I/O performance, namely throughput and latency, and we're going to show you what the differences between those are and how to find them out. We're going to show you some very nice and handy micro benchmarks that you can utilize on your systems in order to measure DRBD performance very reliably and very easily. And of course, we're going to give you some hints and tips for optimizing throughput and optimizing latency for your DRBD setup and for your high availability application. So as I promised, the first thing that I'm going to show you is a very brief recap on how block level replication in DRBD actually works. And of course, as I always say when I do this type of talk, and those of you who have seen me or another Limbit guy present at a conference in the United States, for example, for those of you, those slides are going to seem not that familiar. Is what, as I said, what I always say is this is actually, of course, a simplification of how DRBD actually really works under the hood, but it's sufficient for a general discussion of performance aspects. So what happens if an application, which means anything that uses a block device in Linux, that can be a file system application using a block device directly or another block device, issue a block write right there on a DRBD device. So when we have incoming write I/O, that means that the primary node, remember the primary node is the one that currently has your application running, where your DRBD is writable. When it gets an incoming write, it basically writes that data to the corresponding data block on the disk. It then replicates that write over to the peer node, the secondary node, where it is then written to disk, and the secondary node then acknowledges that write, after which that particular block is, so to speak, cleared or considered in sync from the application's point of view. Of course, this can happen all the time, and it usually does. And the important thing to understand is that from the application's point of view, a block is either being written to both of our nodes or to none at all. Or in other words, as long as an application hasn't been written on the secondary node and has been acknowledged by it, the application doesn't consider it written. That is what we refer to as a synchronous replication. And it, of course, means that DRBD no doubt does introduce some additional latency into the entire setup as opposed to just a standalone disk. And that also affects throughput, but of course it's what buys you high availability. A key performance advantage actually for DRBD in terms of read I/O is the fact that on the DRBD primary node, which is the one that, as you know, has the application running, we can always read locally. This is a key performance advantage over traditional cluster solutions or based on a NAS or a SAN. All of these always have to go through some sort of network stack, be it fiber channel based or be it IP based, in order to read from the block device. For DRBD, that's a different story because, of course, DRBD always reads locally from a local bus, from a local disk, and that's usually a lot faster and also provides better throughput than reading from some network-based device. So when we consider the two aspects of write performance, the first that I'm going to be talking about is throughput. Throughput, or basically evaluating throughput, means to basically write as much data as possible to a particular device in a given amount of time, or to simply write a huge amount of data and then calculate the time that we took in order to write. So what affects DRBD write throughput? There are several factors. Some are in hardware, some are in software but outside DRBD, and some are actual DRBD configuration options. So disk rotation speed is obviously not only one of the most important sources of throughput overhead, but also, as we will see later, an important source of latency overhead. So generally, the faster your disk spin, the better your throughput is, and also the better your latency is, because disk seeks simply don't take as long. The number of stripes in a RAID configuration is one of the most easily tuned factors in terms of DRBD throughput, because generally striping in a RAID configuration, and I'm talking about striping without parity, such as RAID 0 or RAID 1 plus 0 or RAID 10, acts as a throughput multiplier. So, for example, if we're dealing with today's pretty much standard issue hard disks that you can buy that you can get in any server today, you typically could expect something like 50 to 60 megabytes per second of throughput to the actual disk. When you're using striping, that effective bandwidth is multiplied by the number of stripes in the configuration. So, for example, if we had those 50 to 60 megabytes per second to the disk hard drives, and we were using a RAID configuration with 3 stripes, we would get roughly about 100, or we could expect roughly about 150 to 180 megabytes per second throughput from the raw drive. Another factor that greatly affects write throughput is, of course, the use of a controller write cache. As you know, when you are using a write cache on your RAID controller, data that's being written to that RAID array is in fact written to the cache first, which then flushes that data at its discretion. Because you're actually writing to RAM rather than to a comparatively slow disk, and the controller has the option of then flushing into disk whenever it does so chooses, that of course means that you can make your storage subsystem a lot more effective in terms of throughput. However, you should always consider the fact that unless your controller is battery backed, you're putting your data at risk by using a controller write cache. So, or in other words, using a write-back mode for your controller. So the general rule here is, for the sake of the integrity of your data, don't ever make use of a controller write cache unless it is battery backed. And most reasonable or reasonably recent controllers also allow you a configuration setting where write-back is automatically disabled if the controller battery dies, and in that case the controller switches back to write-through mode. And whenever your controller has that sort of option available, then do enable it. Otherwise, you're severely putting your data at risk if that battery dies or goes down or gets depleted at some time. So that much those are a few of the factors that affect DRBD write throughput from the end of the disk I/O subsystem. But then, of course, also we have this other aspect in DRBD, which is, of course, our replication network, which means the typical crossover cable or straight-through cable that we have in a back-to-back connection between DRBD nodes. So the first thing, obviously, is you want to use a back-to-back connection whenever you have it available. You want to use a gigabit Ethernet at least. If you have even greater throughput or greater bandwidth network available, such as 10 gigabit Ethernet, it's a fine idea to use that too. However, if you consider multiplying, or if you want to multiply your replication bandwidth by using NIC bonding, using the Linux bonding module in the balanced round-robin mode, which of course is the only mode that makes sense in this case because it's the only one that can actually load balance single TCP connections across multiple links, because it simply sends one Ethernet frame down one wire and the next Ethernet frame down the next wire. You must understand, or you should understand, that that sort of bonding does not scale indefinitely in terms of throughput. Indeed, because of the fact that NIC bonding is greatly affected by TCP reordering that has to take place on the secondary, for DRBD performance, NIC bonding, and actually not just for DRBD performance, but for general raw network performance as well, bonding does not scale beyond 2 physical links. So in fact, if you get if you've got 2 physical links for your replication network, you can expect about 160 to 170% of the actual gigabit Ethernet bandwidth, so about a 60 to 70% increase. Whereas when you do a balanced round robin across 3 links, you get about the performance or the throughput of just 1 physical link. And if you're using as many as 4, then your effective throughput actually drops below that of a single NIC link. So NIC bonding is fine if you want to get that extra 60 to 70% out of your write throughput, but don't expect anything more from that, and particularly don't expect DRBD replication throughput or synchronization throughput to scale beyond 2 physical links. Then, of course, there are some DRBD options that you might want to peruse in order to tune your DRBD write throughput. For example, the options max buffers and max epoch size. Max buffers is a measure for the amount of memory that we allocate on the secondary for receiving replication traffic. And max epoch size is the maximum amount of data that we allow between 2 write barriers. And those basically should always be configured to the same value. I guess for fairly obvious reasons, it always makes sense for for the secondary to be able to receive just as much data on the replication link as it will write to the disk in one fell swoop. And then there are another couple of options that I want to get into in a little more detail, simply because they seem to have caused a certain degree of confusion on the DRBD mailing list recently. In DRBD 809, we introduced support for flushes on the secondary and on the secondary for actual disk data, and on both nodes for the metadata. A flush or more precisely in the application of the blockdef issue flush function, simply means that the operating system tells its hardware, write this chunk of data to the disk and do not notify me until that, or to more precisely speaking, do not return until that data has actually made it physically to the disk. That is something that we added simply because it is another measure of improved data integrity. But, of course, if you're using something like battery-backed write cache, what that means is that you're, in essence, double-barreling in terms of data security. So we now do have the option of sort of reducing that double security to single security, where we allow to disable these flushes for disk writes on the secondary and for metadata writes in both nodes, because you can rely on your controller write cache to be non-volatile, which means that it must be battery-backed. So again, this is another option. You really don't want to use it unless you're running on battery-backed write cache. Otherwise, you're putting your data at risk, and you should always make sure that performance, even though it's of high importance to you, should always be less of a concern than your data integrity, because after all, you're building high availability clusters for high availability, which ultimately means not losing data. What I've shown you here in the next slide is a brief overview, sort of an example column chart here for write throughput considerations that typically apply to DRBD setups. Depending on your resolution on the monitor that you're viewing this webinar, you might not be able to see the indicators here on the y-axis. Those are supposed to be throughput measures or throughput values in megabytes per second, starting from 0, then going up to 300 megabytes per second. So just in case you can't see that, that's what the indicators here on the y-axis are. And what we have here in blue is a storage subsystem throughput, then in comparison in red, network replication throughput, and then in yellow, the DRBD throughput that we would expect in general from such a setup. The important thing to consider here is, of course, that whatever is slower of either the disk I/O subsystem or the replication network, that's DRBD's theoretical limit. So in other words, DRBD cannot be faster than the replication network or the I/O subsystem, whatever is slower. So consider, for example, what I've got here in the left column group. We have a comparatively slow disk subsystem capable of pulling just about 70 to 80 megabytes per second. Now that would be fast for a single disk, but it's actually kind of slow for a reasonably recent RAID subsystem. So comparatively slow I/O subsystem there with 70, 80 megabytes per second, and we have a fast replication network which pulls about 110 to 115 megabytes per second, which is typical of gigabit Ethernet. Here, of course, the disk is your bottleneck, and DRBD can never be faster than the disk. So if between the disk subsystem and the replication network, the disk is slower, we would then expect DRBD to provide about 5 to 10% less throughput than that disk subsystem. So in that case, we would expect something like 72 to 75 megabytes per second steady throughput. By contrast, consider the middle column. In this case, we have a reasonably fast disk subsystem pulling about 150 megabytes per second. Now, by today's standards, that's reasonably fast. That's not ultra fast. So 150 megabytes per second throughput, and then, of course, your gigabit Ethernet, which will pull about 110 to 115, as I said, will become your bottleneck, and DRBD will not be faster than that replication network, or more precisely, will not provide higher throughput than that replication network. So we would expect DRBD to top out at about something like 100, perhaps 105 megabytes per second. And then the final group of columns would be nicely fast disk subsystem, capable of pulling about 250 megabytes per second throughput. and then a hypothetical network link with about 200 megabytes per second. Here again, our network would be our bottleneck, and we would expect DRBD's throughput to top out somewhere around 180 megabytes per second. So, as I said, what I want you to take away from this chart is the most important thing to understand. Whatever is slower or whatever is worse in terms of throughput, namely the disk I/O subsystem or the replication network, that's DRBD's theoretical limit. And then the additional overhead that we're getting from DRBD is something like 5 to 10% below that. Sorry about that. Okay, and one other thing that I want to mention in terms of throughput before I actually get to a quick demonstration, because this is also sometimes a source of confusion, is how background resynchronization affects DRBD replication throughput. Now again, here's a quick recap on how DRBD works. Of course, on secondary node failure, so that means when our secondary node goes away due to either hardware failure or scheduled maintenance or anything else of that sort. Basically, what DRBD does, of course, the application can continue to write to the primary node, and the blocks that are being modified in the process simply continue to be marked out of sync. Reads, of course, always occur locally, as in the normal mode of operation, which is both nodes online as well. So now, what happens if the formerly offline node returns and now goes back to its secondary role? DRBD does this resynchronization process, which means that the blocks that are marked out of sync are being brought back into sync by a resynchronization process that does not follow a chronological pattern as the blocks were written, but follows the pattern of basically the disks being the blocks being located on the disk. The important thing here is that that replication bandwidth, that synchronization bandwidth can be throttled, and it should be throttled. Replication, which is the synchronous in-time replication of incoming writes, cannot and should not be, and it cannot be throttled, and it wouldn't make sense to allow that because we always want this replication to complete as quickly as possible, because of the fact it is synchronous, anything else would simply slow down our actual application. Whereas background resync is something that can be throttled, and indeed it should be throttled, because if you don't, resynchronization will eat up so much of your bandwidth that the foreground replication will become dead slow or even grind to a halt, at which point your application will be dead slow or grind to a halt. So the recommendation that we always make, and this is also mentioned and described at length in the DRBD User's Guide, is you should always allocate at most 30 to 40% of your effectively available replication bandwidth to DRBD background synchronization. And the way that you do that is using the rate option in the synchro section of your drbd.conf. If you can always change that synchro rate temporarily, if need be. So, for example, if you want your background resynchronization to complete as quickly as possible, and you can't afford it because your actual application is not under heavy load at the time, you can up the synchro rate temporarily by using the DRBD setup synchro command. This is also described in the user's guide, and you can then restore your synchro rate to normal levels when synchronization has completed. If you don't follow these rules, again, your application's performance will suffer because your background resynchronization will eat into your replication bandwidth. It's actually going to bite a major chunk out of it. and that's going to slow down your application. So if you don't do that, if you don't follow these rules, your application will suffer. Please do follow them. So before I get to write latency, which is an entirely different concept, I'm quickly going to show you how we can actually measure that DRBD performance. So what I've got here is I've got a pair of 2 cluster nodes. This is one of our test clusters here at Limbit, and I've got a couple of DRBD devices configured here. And the first thing I'm going to show you is a very, very simple throughput microbenchmark that you can use with that you can run with a tool that is pretty much ubiquitous on any reasonably contemporary Linux machine out there, which is DD. DD offers you this nice opportunity of writing from the 0 device to a particular DRBD device, specify a chunk size or block size at which you're going to write. I'm going to use 1 gigabyte, and then a count, which is the number of chunks that we're writing, which at this time is just 1. And I can also set an output flag, and I'm going to use ODirect for that purpose now. Now, why am I doing that? For one thing, as I said, we're measuring throughput, so what's important here is to write really, really large chunks of data. I'm using 1 gigabyte. Actually, the DD utility will allow you something up to 2 gigabytes. The only thing that's important here is that it has to fit into your physical memory, because if it doesn't, then you're basically just going to run off of swap space, and you're completely going to wreck your results here. So, and by the way, of course, folks, do not try this at home if you have valuable data already on that DRBD 0 device, because obviously this is an intrusive and destructive test. It's going to destroy the data there. So this is the type of performance test that you want to run before you go into production, or if you're already in production, you want to run this on a scratch volume. And this test is going to take a few seconds, obviously. And I'm already getting pretty good performance here on this device. I always want to encourage you to run this test when you run it at least 3 times, just to get a bit of a statistical average there. And with 96 to 97 megabytes per second, we're actually quite good already, but not quite there yet, because we're running here over a gigabit Ethernet link, and we're running on a really, really fast storage subsystem, which is capable of pulling about 250 megabytes per second. So what I'm going to be doing is I'm going to tweak my DRBD here a little bit. Hang on a second. I'm going to show you something first. So let's quickly dump the current configuration for that device and show off the DRBD setup show command for those of you who haven't seen it. So what we're seeing here is this is basically all at its default settings, and a particular throughput killer here in this configuration is the AL extents 127. I'm not going to go into much detail what the activity log, which is what AL stands for, is, and what it means in detail to set these AL extents. If you're interested in some background information on that, I would encourage you to read the part named DRBD internals in the DRBD Users Guide. There's a section on the activity log there where this is described in considerable detail. But let's just, what I can tell you here is that the smaller our activity log is, the faster our resync time after our primary crash is, but it affects our throughput sort of negatively. So we will tweak that real quick. And that goes here in the syncer section. And I have that defined here for all of my resources by defining it here in the common section. Now, of course, what I have to do is I'm going to have to SCP my DRBD conf over, and I can now run the DRBD atom adjust command to adjust the syncer rate. And I can add the dry run flag here just to see what DRBD atom is going to be doing. So in this case, it's just going to adjust that syncer rate here. And now I'm going to be running that exact same test again that I just ran. And here's another interesting aspect of this micro benchmark, or rather an interesting aspect of DRBD. Whenever we freshly reconfigured an activity log, such as what we just did, the AL is what we consider cold. So this is a typical, sort of a cold cache effect that we're always getting here when we've recently modified the AL. So that means that the first reading that we're getting from this micro benchmark is actually severely underperforming. Actually, it looks like it doesn't change anything. But then the subsequent runs provide acceptable results. And that's another thing that you always want to do when you run this micro benchmark is run it about 3 to 4 times and always discard the first result, because the first result that you're going to be getting is always going to be greatly influenced by having a cold activity log. And with that, we've already maxed out our expected gigabit Ethernet bandwidth here, and went right up there to 114, 115 megabytes per second. So that's something that we can be very happy with on that hardware. And we've managed to squeeze out the last little bit of performance right there out of this DRBD setup. So being happy with that, I'm now going to continue with a quick discussion of latency, which is an entirely different concept. Latency means, hang on a second, I don't think you're seeing this slide now. So write latency is something different. Write latency is not write as much data as you can in the shortest possible time, but write a tiny little chunk of data as fast as you can. And in fact, before I get into what affects the DRBD write latency, let me quickly skip back here. I want to add a few more points on what does this tiny chunk of data actually mean. Well, a tiny chunk of data in this case means at least 512 bytes, because 512 bytes is the hard sector size in Linux, and no application can ever write to a block device in increments smaller than 512 bytes. If you tell an application to write to a block device something like 2 bytes or 3 bytes, what it's going to be doing, it's going to be reading an entire sector into memory. It's going to splice those 2 or 3 bytes right in there, and then it's going to write it back to the disk. So what you're doing there is actually a combination of reading and writing. That's not a definition of write latency. So write latency in DRBD means write 512 bytes of data as fast as you possibly can, Or that tiny chunk of data can actually be a little larger as well. So if you're using something like a block-based file system such as ext3, and you're using a block size of 4K, then that 4K is the smallest chunk of data that's ever going to be written to that DRBD device. So that's just for introductive purposes. And then again, what affects DRBD write latency? Disk rotation speed, again, tops the list. This is not in order of importance, by the way, but still we have disk rotation speed right there in that list as well. For, I guess, fairly obvious reasons. The rate level that you're using in a rate configuration, needless to say, always affects DRBD write latency as well, particularly the question of whether you're using a rate configuration with parity, such as rate 5 or 6, as opposed to a rate configuration without parity, such as simple striping, rate 0, or striping with mirroring, which is rate 1 plus 0, or rate 10. Your controller write cache, again, is a great latency minimizer. Again, I want to reiterate and stress, don't ever use a controller write cache in write-back mode unless it is, in fact, battery-backed. And if it allows you to automatically switch back to write through if the battery dies, do use that option. Replication network latency is another factor. The replication network latency basically is dependent on the replication protocol, or actually data link layer protocol that's being used. As we'll see shortly, Gigabit Ethernet is actually, in some configurations, comparatively slow. Then again, the DRBD options, no disk flushes and no MD flushes, for the same reasons as discussed earlier, and also the activity log size. In terms of the considerations that apply to write latency, consider this little, sort of time diagram. The axis on your left is your time. The distance between those two nodes is completely irrelevant. It's just there for optical purposes. Now consider what happens if an application actually writes to a DRBD device. What happens fairly simultaneously is we're writing to a disk. This typically takes a comparatively long time. And we're replicating a packet over the network, which typically takes a short time. So if we're writing to an actual physical disk, a typical disk write would be something like 0.3 milliseconds or 300 microseconds. I'm sorry, of course, 3 milliseconds. And a typical network replication packet would reach the peer in about 100 microseconds. So 3 milliseconds versus 100 microseconds. The disk write completes a lot slower than the actual network replication packet takes to travel to the secondary. What happens next is the secondary writes to the disk. So we have a bit of an overlap in the timing here for the disk write, and then we send the network acknowledgement back. And the resulting gap between the single disk write and the complete write for DRBD, that is DRBD's introduced latency penalty, as opposed to just a single standalone disk. That latency penalty, in those types of configurations, writing to a physical disk and replicating over Gigabit Ethernet, can range anywhere between 7 to 20% in a reasonably configured DRBD setup. However, if we introduce a write cache to the setup scenario, and indeed you should, if it's battery backed, then it looks a little different. And here we are at the about 300 milliseconds I erroneously mentioned earlier. This is where they belong. I'm sorry, microseconds, of course. We would have disk writes, or so-called disk writes, in fact, they're controller writes, that are well under a microsecond. Well under a millisecond, I'm sorry, I'm getting my SI units messed up today. And we've got network replication, which is unchanged. And so what happens here, the disk write, of course, the controller write, in fact, on the secondary completes, of course, just as fast as the one on the primary, and then we sent our network acknowledgement back, which takes us just as much time as it used to if we didn't use battery back write cache. And now, all of a sudden, even though the whole process completed a lot faster, our latency penalty in terms of a percentage as opposed to the single disk write is a lot larger. we might be talking about a latency penalty of something like 120 or maybe even 200%. So duplication or maybe trifold latency increase. What is the moral of the story that you can take away from this? Well, to a certain extent, of course, percentages lie, because in this case, that huge percentage increase, in fact, corresponds to a huge decrease in total latency by introducing a battery-backed write cache. And what it also means is there's not really that much you can do about that unless you are using something other than gigabit Ethernet. It also means that, of course, bonding, which has these TCP reordering issues, affects latency, or has the potential of affecting latency issues in DRBD greatly. There will very shortly be support in DRBD for network replication protocols, with much lower latency than gigabit Ethernet. So do stay tuned on our website for that announcement, and undoubtedly that will also be on the DRBD user mailing list and various other channels. So let me skip back to my demonstration window here. Again, very, very simple benchmark, indeed almost identical benchmarks. I'm just changing a few parameters here. So instead of writing a whole chunk of 1 gigabyte, I'm using these very small sector size writes, 512 bytes, and I'm going to be doing 1,000 of them. And here what we can see is exactly what we would expect here from DRBD. And that is, in fact, just what you would expect in terms of latency. Consider this change here. Here I'm writing to the lower level device of this DRBD resource. Folks, again, don't try this at home. This is even more destructive than the earlier test. Now I'm basically writing underneath DRBD, so whenever you do that, that definitely requires a full resync afterward, or when you want to put production data on it. This is, of course, a lot faster. So here I'm writing to the lower level device, completing 1,000 writes in 0.093 seconds, which means one write took me about 0.093 milliseconds, or in other words, 93 or about 100 microseconds. And then DRBD adds exactly that gigabit Ethernet latency of about 100 microseconds per trip to that number. So this is precisely what we would expect here. If you're seeing these results, you're perfectly fine in terms of DRBD on gigabit Ethernet as of now, and there's not really that much that you can do about it. But as I said, stay tuned for announcements in the very, very near future on our website for much, much lower latency DRBD applications and network replication protocols that are going to be supported. And then to round out the talk, I want to mention a handful of other factors that you might want to consider when deploying your high availability application built on DRBD. So whenever you've got a file system layered on top of DRBD, which I would assume would be the majority of use cases, it's always a smart choice to use mount options that are helpful to avoid unnecessary disk writes. So in particular, you want to use mount options like no A time and no direct A time, because otherwise, on every access to a file, or every access to a file, either on every access to a file or on every access to a file or directory, you're going to get modifications to the access times, which means a disk write, which means that if you're not using this access time for any reasonable purpose, it's a completely unnecessary disk write. So you can simply do away with that by using these mount options. If you are running on a fast RAID controller with Batteryback write cache, the distribution of your choice may not use the ideal I/O scheduler, also known as an elevator, for its block devices. Notable examples here are SLES and REL. Both of these, in recent versions, use a CFQ scheduler by default, which is great for desktop applications and which is great for, should I say, lesser quality storage controllers. But if you have a really fast controller, good latency, great throughput, and reasonable caching, then it usually makes much greater sense to resort to either the deadline I/O scheduler or perhaps even the no-op scheduler. Ubuntu, by the way, has this right to an extent because they provide separate desktop and server kernels, and the server kernel has the deadline scheduler enabled by default. If you're curious as to how to change those scheduler settings, you can either do that using sysfs, or you can do that by using a global system default by passing the elevator kernel option on boot. And then, of course, another thing is you may want to use read ahead with care because it may backfire, particularly if you have latency critical applications such as databases. It may make absolutely no sense for your database application to write a whole stripe of perhaps even something like 64 kilobytes of data if all it wants is a memory page of 4K. So those are just a few other factors that you may want to consider in setting up your DRBD-based HA solutions. And what I want to reiterate is, don't forget this. I call this the golden rule of storage. Whatever importance that you assign to performance, data integrity always goes first, and performance should be your second concern. Perhaps a close second, trailing data integrity by a small margin, but it should be the lesser of your concerns. Data integrity is what's the most important. If you have any further questions or queries, or you want to get in touch with us, or book us for training, hire us for consultancy, get a support contract, or anything else, then do contact us. The best way to do that is to go to our website, and hit the contact form. I've put up a direct link here, which is www.limbit.com/en/contact. Just leave your name, your email address, or a callback number, and the Limbit service that you're most interested in, and we will be in touch with you very, very shortly after that. Of course, the DRBD user mailing list is always a great resource for discussing performance issues. So if you're not subscribed yet, then please do. That is DRBD user at list.limbit.com, or just go to the web interface at list.limbit.com and subscribe to DRBD user, which indeed you will have to do before being able to post. The three of us, Brian, Kevin, and Smith, are going to be hanging around for another 15 to perhaps 20 minutes after this presentation. So if you have any other questions that you want answered right now, then please don't hesitate to ask. For now, I thank you very much for your attention. I do apologize for the audio issues that we had at the very beginning of the webinar, and I do appreciate your cooperation for signing out and signing back in. We hope that this won't happen again next time. And a recording of this webinar will shortly be available from our website, which of course is www.limbit.com. Go to training, and from there there's going to be an item, a navigation item that says recorded webinars, and there you're going to be able to download a recorded version of this webinar, and that of course will be free of charge, just like this webinar is. So again, thank you very, very much for your attention. We're going to be closing the audio broadcast and the teleconference if you're logged in via SIP right now. We have a question for you, a survey question as you sign off regarding the audio quality of this event. So please give us your feedback on that, because we had some issues there with the last webinar we did. And now, again, and for the final time, thank you very much for your attention. We're closing the audio broadcast right now, and we'll be hanging around for the next 15 to 20 minutes for your questions.